voxel data. In this session, we will show you the use of voxel data in ArcGIS Pro. We will review workflows to create your own voxel data, and we'll see some examples from our customers and partners. This webinar is designed for anyone interested in learning about the new capabilities in ArcGIS Pro for working with complex 3D data. I'm Paul Schwandt, an Associate GIS Analyst out of the Esri Canada Vancouver office, and I'm joined by my colleague Sapita, who is about 1,000 kilometers away from me in Calgary. Thanks for joining me, Sapita.
Hi, everyone. It's a pleasure to be here. Thank you for having me.
For those of you who haven't attended one of our webinars, we are recording the session and we'll email you the recording along with the slides after the webinar. We've made sure to include a lot of links and resources in this PowerPoint for your sake. If you have any questions about the content we are presenting, please use the Q&A panel. Be sure to ask all panelists, type your question in the box, and click send. We will take questions at the end, but feel free to type your question in at any time. If Sapita and I can't take your question during the webinar, we will follow up with you afterwards. So today's session will focus on several topics. Firstly, we will introduce the benefits of using voxel. Then we will learn workflows to create voxel layers in ArcGIS Pro. And last but not least, we will demonstrate some of the best practices to get the most out of this new type of data. I hope you enjoy and find this webinar useful. ArcGIS Pro 2.6 with an advanced license comes with the new voxel functionality, allowing you to visualize 3D data grids with billions of voxel cubes. Voxels created from NetCDF data will allow you to visualize and convey critical information for climate change modalities, marine ecosystems, atmosphere, or geological phenomena, helping us cross the digital divide of continuous space-time data and spatial objects in a GIS. We are only in the beginning stage and initial launch of the voxel user experience in ArcGIS Pro, but so far we can already create, analyze, and leverage this type of data using filtering, symbology for 3D visualization, time animations, and other interactive exploration features. In this initial launch, voxels are limited to a desktop experience in local Cartesian scenes. However, Esri is planning to enhance this experience on the web and across ArcGIS in the future. Next year, we will see some more enhancements for working with the voxel. But for now, this is a great way to understand large sets of volumetric data that you may have in your organization or any that you might want to make. So let's first understand what voxels are. A voxel is a combination of the words volume and element, representing values on a rectangular prism in 3-dimensional space. This is analogous to a pixel, which represents 2D image data. A voxel layer represents multidimensional spatial and temporal information in a 3D volumetric visualization. Voxels have unique or continuous values. They can contain one or more variables, and depending on the type of data represented by a voxel variable, you can visualize qualitative discrete or quantitative continuous data. With voxels, you can visualize atmospheric or oceanic data, a geological underground model, or space-time cubes. Access to volumetric space-time information about the world provides higher accuracy in analysis and a better understanding of conditions you can't physically experience. So use voxel layers to explore spatial relationships with other spatial content. For example, compare an underground geological voxel along with some borehole data or a BIM construction model that is planned for the area. Voxels can also include a time dimension. A voxel layer enables the visualization of time as a fourth dimension, X, Y, Z, or T, or where time represents a third dimension, as in space-time cube, X, Y, and T. Voxels do not need to be continuous in time or extent. You may have multiple voxels occupying the same space, but occurring at different times. Voxels can also be elongated in one dimension. They're not required to be perfect cubes. Which dimension is elongated just has to be uniform across all the adjacent voxels. This is shown in the lower image on this slide. In ArcGIS Pro, it is also possible to apply a vertical exaggeration to your voxel layer, scaling its height by a factor that you set. We already see many different applications of voxels across many different industries, and we believe that voxels will be useful to many more. Some of the common industries where we see voxels are in the natural sciences, especially oceanography, geology, and the atmospheric sciences. Voxels have also been applied in the extractive industries, such as oil and gas and mining. We can also foresee the application of use of voxels in architecture and engineering construction industries, such as visualizing soil layers underneath construction sites or analyzing the volume of green spaces. We predict there will be many more applications for voxels with many different industries and scientific visualizations that are not listed here. In ArcGIS Pro 2.6, there are new UI experiences that allow you to create, manipulate, visualize, and explore voxels. You can adjust the display and appearance of a voxel layer by changing the offset, vertical exaggeration, and the variable used, the symbology, as well as manipulate lighting options on your voxel layer. You can represent voxel layers as a volume or surfaces. If you are visualizing a continuous variable, you can create an iso surface to explore a specific value as a surface. You can also define an area of interest using slices or create sections to explore different locations of the voxel layer in greater detail. NetCDF is a file format for storing multidimensional scientific data such as temperature, humidity, pressure, wind speed, and direction. Many organizations and scientific groups have adopted NetCDF as a standard way to represent some forms of scientific data. In ArcGIS Pro, you can use the data menu item to add the multi-dimensional voxel layer to your local scene. Voxels in ArcGIS Pro support CF-compliant NetCDF datasets with XYZ, XYT, or XYZT data. You can find out more about CF conventions in the URL at the bottom of this slide. So now Sapita is going to show you an interesting example of visualizing and exploring voxel data.
Thank you, Paul. In this demo, I want to show you how we can serve. This demo will serve as an introduction for adding voxel data into a local scene. It's a great example to understand NetCDF data and accessing it directly from its source. It shows our ability to read the scientific data, in this case, discrete soil types underneath the surface. This layer is an underground model of Netherlands. This geotop model comes from the TNO Geological Survey of the Netherlands. One of the strengths of voxel layers is the ability to show an enormous amount of data all at once. We are looking at 5 million voxel cubes of 100 per 100 meters and a depth of half of meter. Each voxel contains information on type of soil for the whole of the Netherlands. As you notice, this is a local scene. A voxel is required to be in Cartesian space. Let me show you how we can add this voxel layer in our local scene. Only at Pro 2.6 we can find the option for adding multidimensional voxel layer. Voxel layers are based on volumetric data stored in a NetCDF file in ArcGIS Pro. This dialog box helps us to find a NetCDF file. And as you see, it has NC extension and almost 30 gigabytes of data. That's huge in terms of our volume here. The next step is adding the default variable, and we want to represent little classes as a unique value in this sample set. Now, 30 gigabytes of data will load into memory and we can visualize it here. You can change and adjust the display of a voxel layer by changing the offset, vertical exaggeration, the variable used, and the symbology. You can always manipulate lighting options on your voxel layer here. When vertically exaggerating a voxel layer, its height is scaled by the value you set for the vertical exaggeration property. Let's explore layer symbology. The data is visualized as unique values because the voxel layer contains qualitative data. You can set the variable and define the appropriate symbology. You can also edit labels and colors. I've already undertaken some symbolization of this data. Let me turn off this layer and switch to our previous layer. I've already enhanced my layer with a proper label name and appropriate color scheme for each soil type, just for the sake of time. What we are able to see here is the separation of the lithography types. If I'm getting close enough, it almost looks like one of my kids' Lego sets. You can see how this voxel is gridded and has multiple depth dimensions. One of the exciting soil types in Netherlands is peat. It causes land subsidence. Having this information before starting a construction project is very valuable. One of the other possibilities with this data set is the ability to filter the district values like peat. In this way, I can evaluate the amount of peat in the Netherlands. One of the things that will help us in this kind of exploration is to use our slice tools. You can use slices to define an area of interest in a voxel layer. You can apply a horizontal slice to reduce the voxel layer to a specific height. You can go to the slice positioning and create a slice at various depths. We can see based on the depth what the lithography types are available in the subsurface. Also, I can go and slice differently from the side. A slice of voxel layer vertically provides a bit of different kind of experience here. Another exciting thing is the ability to save voxel as a layer file or layer package. Either way, it will produce a layer file that can be shared with the members of your organization. Please keep in mind that this is the first release cycle and more capabilities will be added to the Voxel in the next release. Let's move on to the next demo. In the second demo, I want to show you how you can explore the voxel data that is time-enabled. Now we are looking at a voxel layer for the water temperature in the Atlantic Ocean that comes from NOAA, National Oceanic and Atmospheric Administration. In the previous example, we look at three-dimensional data, X, Y, and Z. But voxel layers can also show four dimensions, X, Y, Z, and time. Let's take a closer look at what we have on this map. I'm using the country polygon feature class that has been extruded to the specific value to match its Z coordinate exaggeration mode with the voxel layer's exaggeration value. You can use this method to combine and align your feature layer with your voxel layer. Because this data is time-enabled, the Time tab will be showing up on the map display. Another fantastic thing is we can showcase incremental time through the time slider. Playing the time slider, we can see the warmer water represented by pink, red, and yellow pushing north in the summer, showing the Gulf Stream's influence. This is the best way to create a video of your voxel data movement using ArcGIS Pro. We can filter the colder water using the transparency function in the symbology pane. You can interactively change the control points position by moving them on the transparency function graph. As a result, the warmer temperature, which is on the top, shows up in the map display, and cooler temperatures toward the ocean floor are disappeared. We can always toggle through these time intervals using the time slider to see how this warmer water moves toward our border in Canada. Let's take this transparency off and look at color range option to adjust the temperature using mean and max range options. In this way, I can see the range of temperatures between 15 and 22 degrees Celsius, the optimal temperature for some fish species. Now, the time slider can give us a little more control to see the water temperature range. Voxel data allows us to look at the data in so many ways, like defining isosurface. An isosurface is a surface representing a specific value within a continuous variable. For example, you can visualize a threshold value for the ocean's water temperature as an isosurface. This allows you to identify the location of critical value. You can change the value dynamically using the voxel exploration pane. By default, an isosurface color matches the color in the symbology color scheme for the specific value. Now, let me show you how we can create isosurface. We can create isosurface by right-click on the isosurface and selecting the Creating an Isosurface option. This enables us to choose a temperature break value like 13 degrees Celsius. Using animation can quickly provide some feedback in terms of these isosurfaces. It's beautiful to see how quickly we can render this data unencumbered by geometry. We are looking forward to seeing what you will do with time-enabled voxel layers. Now it's time to move on to the next demo. In this demo, I want to show you how you can compare two variables in one voxel data. This time, we are going to look at ecological marine unit created by USGS. For this demo, I would like to compare the temperature variable with the fractional saturation of the oxygen variable, and I wanted the fractional saturation of oxygen as my default variable. Before I go any further, I would like to change my oxygen saturation schema to a color scheme designed to represent oxygen. Now, I want to create sections for oxygen saturation and lock the sections to compare it with the temperature at a specific threshold. Let's create a vertical section close to the equator. And I will make another one close to the Pacific coast. Now I can right-click on the sections and lock the sections. By locking the sections, they always will be available even I change the variable. To switch the variable, I'm going back to the Appearance tab and selecting Seawater Temperature. As I said, I would like to compare oxygen saturation with the temperature. For that, I'm creating two isosurfaces at 20 and 25 degrees Celsius. Let's look at isosurface with 20 degrees Celsius temperature. And also, I would like to create another isosurface that represents the 25 degree Celsius temperature. Because the colors of both isosurfaces are very close together, I can change the color scheme and its transparency to differentiate them and make them more visible. Now I can see the spatial relationships between oxygen saturation and sea temperature at 20 and 25 degrees Celsius. We can see those areas with less saturation of the oxygen have warmer sea temperatures. I hope you use this workflow to explore two variables in your Voxel data. Now turn it back to you, Paul.
Thank you, Spida. That was great. So now in the second part of the webinar, we will show you how to create your own voxel data using geostatistical analysis tools in ArcGIS Pro. So the first way to create a NetCDF in ArcGIS Pro for voxel visualization is to use the empirical Bayesian Kriging 3D tool, followed by the GA layer to NetCDF tool. The empirical Bayesian Kriging 3D is a geostatistical interpolation method to interpolate 3D data points. All points must have X, Y, and Z coordinates and a measured value to be interpolated. The output is a 3D geostatistical layer that calculates and renders itself as a 2D transect at any given elevation. You then follow that with the GA layer 3D to NetCDF tool. With this tool, you can export one or more of these 3D geostatistical layers to a NetCDF format to be used for visualization as a voxel layer in a local scene. Interpolating 3D points into your own voxels is great for many workflows. For example, oceanographers could create voxel volumes of dissolved oxygen and salinity using sample points at various ocean depths. Atmospheric scientists could create volumetric models for pollution and greenhouse gases throughout the atmosphere. Or geologists could take borehole core data to interpolate volumetric visualizations of subsurface geologic properties, such as mineral concentrations or porosity. The second way to create a NetCDF for voxel visualization is the Create Space-Time Cube by Aggregating Points, GP tool. This tool summarizes a set of points into a NetCDF data structure by aggregating them into space-time bins. The best use of this workflow is when you have point features with a timestamp, such as crime data. You can aggregate this data into space-time cubes to better understand the spatio-temporal patterns throughout your study area. This tool does require projected data to measure distances accurately. So now Sapita is going to show us some really interesting examples of creating voxel data in ArcGIS Pro.
Thank you, Paul. The oxygenation of the oceans is one of the most important issues in oceanography today. To tackle these difficult problems, scientists must be able to make accurate three-dimensional models of dissolved oxygen levels in the oceans. In this demo, I will show you how to perform a 3D geostatistical interpolation to predict the oxygen levels throughout the entire Monterey Bay, California. We are looking at dissolved oxygen measurement taken at various depths provided by NOAA National Centers for Environmental Information World Ocean Database. The oxygen points are symbolized by their oxygen level, with the lowest measurements displayed in blue and the largest measurements shown in red. A histogram chart allows you to explore the distribution of our data. Also, we can use a scatter plot to visualize how the oxygen levels change with depth. We see the oxygen level is highest near the surface and then drops quickly. Next, we use the empirical Bayesian Kriging 3D geoprocessing tool to interpolate the dissolved oxygen measurements into a continuous model that predicts dissolved oxygen everywhere between the measured points. I've already added the oxygen prediction geostatistical layer to the map. Let me show you the output of this tool. And here you go. But let me highlight a best practice here before we move on. We set the vertical exaggeration on our layer to match the vertical exaggeration of the base map and sample oxygen points. The 3D geostatistical layer automatically enables a range slider. This color scheme uses red to indicate areas with predicted oxygen levels above 3.7 micromoles per liter. To visualize the dissolved oxygen prediction as a voxel layer, we use GA Layer 3D to NetCDF2. This tool allows you to export the dissolved oxygen predictions to NetCDF format. You can provide the separation between these gridded points using the X, Y, and elevation spacing parameters. The tool takes a few minutes to run, and I've already done it. The voxel layer is added to the scene, and let's look at it. Initially, the voxel layer doesn't have the same vertical exaggeration as the rest of the scene. We can adjust its properties by changing the exaggeration number and the exaggeration mode to Z coordinates. As you see, the voxel layer fills up a full 3D cube. But some of the areas of this cube don't have any oxygen measurements. We will use slices to remove two corners of the voxel layer that don't have points nearby. You always can use the flip tool to look at two of the corners of the voxel layer that have no oxygen measurements and have been removed from the voxel layer. Another way to look at this voxel is through isosurface. Isosurfaces are the 3D equivalent of contours. A contour is a line where all locations on the line have the same value. Similarly, an isosurface is a shell in 3D where all locations on the shell have the same value. In this case, the same dissolved oxygen level. I hope this demo encourages you to try empirical Bayesian Kriging 3D on your data. Now it's time to move on to another demo. In this demo, I wanted to show you how you can use data gathered at boreholes to create 3D empirical Bayesian Kriging layers and then export that as a NetCDF to be viewed as a voxel. I love this demo because it shows how voxel and beam data can help us explore and interpret subsurface information. We are looking at Houston International Airport, a building scene layer created from Beam Revit. Let me give you a little background about this demo. Houston is built on a riverbed. One of the issues associated with this building is that there are multiple layers of sands and clay, as riverbed deposits affect the subsurface structure of the built environment. So we need to get an accurate picture of that soil density. For that, we will bring this borehole data first, and you can see the individual points of collection. This layer is symbolized by SPTN value, or soil density, that ranges from 0 to 1. And as you see, the densest location has a darker red here. We need to interpolate these values using a 3D empirical Bayesian kriging tool. Let's review some of the parameters. We are bringing that borehole data in as the input feature. The elevation field contains each input's elevation value. The value field contains the density of soil that we are interpolating. The output gives us the interpolated result. Let's take a closer look at the output using the range slider and quickly move through some of these values. You can see the interpolated surface that helps us understand the predicted soil density based on their Z values. In this range slider, we are focusing on a single set here, but we can widen that range up to see the values outside of the minimum and maximum ranges. This is great, but we need to visualize the dissolved oxygen predictions as a voxel layer. To do that, we use GA Layer 3D to NetCDF tool. This tool will take that empirical Bayesian kriging 3D layer as an input and create a NetCDF file that will contain the soil density values from the input layer. We define X, Y, and elevation spacing. These parameters specify the distance between each gridded point. We also select prediction as the output surface type. Let's look at the result. Adding this NetCDF as voxel to map display allows us to see and explore a full 3D cube of the predicted soil density. Let's take a look at its symbology. We already modified two things in the symbology pane just for the sake of time. We changed the color range setting to define a better color range and use the transparency function to filter and highlight the tough and dense soil type. We have values from 0.11 to 0.99, and one represents tough and dense soil type, and transparency function can highlight this value. Let me show you another way to explore this data. Right now, we are just looking at this voxel only from the side, but it might be an excellent case to use a vertical slide to get the closer details in this way, and we can see how riverbed deposits affect some of the subsurface structure over time. You see how easy we can explore the subsurface information under the ground using 3D points, and beam Revit information. We are looking forward to seeing what you will do with voxel layers. Now it's time to move on to another demo. In this demo, we explore the social distancing data and some of the impact of the COVID pandemic on travel patterns in California. This map shows social distancing data symbolized by the percentage of staying at home behavior field from May 1st to June 14, 2020. Data clock can provide a view of cyclic patterns of stay-at-home behavior. In this chart, each ring represents a week and each segment represents a day. This chart shows Sunday tends to be a popular day for staying at home. To visualize the data as voxels, we need to create a space-time cube from this social distancing data. This tool will bin and aggregate feature data into a space-time cube stored in the netcdf data format. We chose 1 day for the time interval and 5 miles for the distance interval. We added other fields available in this layer as variables. Let's take a look at the result. In this volumetric visualization, earlier temporal bins are on the bottom and more recent temporal bins are at the top. Areas with higher stay-at-home percentages are represented in blue and areas with the lowest stay-at-home percentages are presented in red. We applied the transparency symbology to make the more extreme values stand out in the scene view. This helps visualize the higher and lower stay-at-home values. We can use slices through the voxel layer to see the values in the middle of the data volume. Visualizing trends over time in this way is a great way to see the entire picture, especially. The voxels in each column correspond to time slices at each location. Since lower voxels are older, you can read up a column to see how behavior has changed at a given location. For example, if a column starts dark blue and gradually transitions to lighter blues, pinks, and dark red, you can assume that there has been a trend to less stay-at-home behavior at that location. These techniques can help you explore and understand spatiotemporal trends in a complex data set. We hope you apply these techniques to your own spatiotemporal data. Last but not least, let's move on to another demo. Let's look at another example of creating voxel data, this time using big data. We are looking at Toronto parking ticket tags that have almost 2 million records. This data is a temporal data set, and we are going to use its datetime field in the Create a Spacetime Cube by aggregating points tool. Let's look at this tool. This tool aggregates these parking ticket tags into space-time bins. The output from this tool is a netcdf. The time step interval defines how we wanted to partition our aggregated points across time. In this case, we aggregate points using a 1-day interval. And we choose fishnet grid for aggregated shape type, and the distance interval specifies how large the space-time bins should be. We make each fishnet bin 1,000 by 1,000 feet. Okay, let's look at the result. We get a big blue block that is surrounded by the value of 0. Let's work through it using the symbology pane. I will choose another color scheme, blue to red, which is more acceptable for this type of data. But I can also switch the color ramp so our icons become red. Next, I'm going to take our significant date range off and extend that color range so that I can see the color range from 0 to 173. In this way, we can see the bins with 173 parking tickets per day within a 1,000 feet grid. We are going to use transparency function to subtract quite a bit of noise, and I bring these low values down and focus more on the reds. I will bump the minimum color range up to 4 to show some of the cubes that their value is significant. Let's experiment a little bit here with the maximum color range, and we want the bins with more than 90 parking tickets to show up in the red colors. To make sure that all the cubes are above the ground, we set an offset here at 100 meters. Let's have a closer look to check if more red came out through. Every flat plate we see here represents the number of parking tickets per day. Let's take some other exploration here. In this case, isosurface can help us to understand more about this data. It's interesting to find a surface that contains 20 parking tickets within a day. I hope these examples give you an idea of creating Voxel, especially when working with a big data. Now, let's start and talk about the next part of our webinar, where we are going to show you the best practices we need to know about the Voxel data. In this session, we are going to highlight 5 tips that answer some of the common questions you may have while working with the Voxel data. Let's look at the tip number 1. One of the issues we may encounter is that the Add Multidimensional Voxel Layer dialog box doesn't recognize our netcdf file. And you may wonder why. The answer is unsupported netcdf files don't display variable information in the dialog box and cannot be added to a local scene. A warning button usually appears on the dialog box. When you click it, you can see a report on any issues with the netcdf file. Always ensure that your netcdf file is volumetric and contains the necessary X, Y, Z dimensions. Let's move on to the tip number 2. The second common issue is when we receive a notification that our Voxel layer will not draw. To solve that, ensure both the Voxel layers' horizontal and vertical coordinate systems match the scene coordinate systems. Tip number 3. If your netcdf file has the wrong coordinate system, place a projection file with the same name as the netcdf file in the same directory to override the coordinate system of your netcdf file. You can save any coordinate system as a projection file. Let's move on to the tip number 4. The below ground navigation is disabled by default in your scene. This helps you avoid accidentally navigating underground. If your scene contains underground or subsurface data, for example, pipelines or geologic bodies, you should enable this capability. To enable that, select the ground elevation surface in the Contents pane. Then on the Appearance tab, in the Surface group, check the option Navigate Underground. Let's move on to the last tip, but not least. You can use Python to transform your data into a voxel-compatible format by combining individual time-stamped files into a single data source. In this way, you can change its data dimensions or correct its altitude orientation. You can find the Python code in the blog post of 3 ways to prepare your data for the Voxel layer. You can find the blog post link on this slide. Paul is going to show us how we can use this Python code in ArcGIS notebooks to transform data into a voxel-compatible format. Okay, turning to you, Paul.
Thank you, Spina. So voxel layers take a specific type of NetCDF data as its input. The NetCDF format offers a lot of flexibility in terms of its data storage structure, but this means there's always not a lot of consistency between NetCDF data sources. So you may need to process your NetCDF data to make it compliant with ArcGIS Pro requirements and for it to visualize correctly as a voxel volume. So this demo contains some examples of using Python to edit NetCDF files. With just a quick few lines of code, you can make your data compatible for voxel visualization. So in this demo, I'll be using the Jupyter Notebook environment in ArcGIS Pro. So NetCDF data often comes in separate files that span over different timestamps or height stamps. And to visualize this data as a voxel layer, you will need to combine it into the same file. So in this demo, I have annual max temperature files from 2000 to 2020. And I want to combine them into the same file. So the first thing I want to do is to import the Xarray library and the NetCDF4 library, Python packages. So Xarray extends pandas and NumPy, and it's for working with multi-dimensional data sets. And then first, we want to load in a single file to check its dimensions. We want to confirm the name of the time dimension. And we can do this by just loading it in and checking this Xarray object. So we can see here that the time dimension is called time, which is lucky, but this is not always the case. We can also see that there are 366 time values in this single NetCDF file. So next, we want to open any NetCDF file in my folder that begins with Tmax. And then we want to combine this data using the time coordinate dimension. So in these dataset files, time is the dimension that defines the relationship between this data and its order in respect to one another. So when we use this open dataset, we want to combine by chords and concat dim by time. So time will be the dimension that it's concatenated by. Then we can just see the results. So we can see now that all the files in my directory are represented in this Xarray dataset object. And we can look here. It still has the same coordinate values, except for the time dimension, and there's now many more files. So now we're done. All we have to do is take this object and we can output it to our directory as a new NetCDF file. And then we can input this into ArcGIS Pro for voxel visualization. So also when you're working with voxels, you may run into the issue where you go to add your data using the multi-dimensional voxel layer. and no variables appear in the dialog box. So why does this happen? So you need to make sure that your netcdf file is in a supported format. It has to be both volumetric and contain the required X, Y, Z, or T dimensions. So the particular error that my data had is that the order of the dimensions was not supported. So CF compliant netcdf data does not have particular restrictions for the order of the dimensions, but ArcGIS Pro does. So we can transpose or change the order of the dimensions in the data to an order that the voxel layers accepts. So we can just open this file with X-ray here, pointing to my data set. And we could see here, this is the order of the dimensions. And we can see that, and this is not an order that ArcGIS Pro supports. So it's law and level lat time. So we will need to apply the X-ray transpose operation to reorder the data either as longitude, latitude, level time, or time, level, lat, long, which are supported formats in ArcGIS Pro. So we can just run this here and then relook at the results of this X-ray data set. And we can see now our dimensions are in a supported format. So then we can use this new file. As before, we can just export it as an netcdf, and we can add it into our local scene, which I've done already, and then it works as a voxel layer. So this is just a couple quick ways to work with netcdf files using Python. So working with a Python package like Xarray, there are many more ways to process, modify, or create your netcdf datasets for working with voxel layers. Thank you. Back to you, Spida.
Thank you so much for the great demo. Okay, so what's next to voxels? This is our first experience working with voxels in ArcGIS. Well, Esri has been working on this capability for several years, and this is the first time that Esri will be able to put this to the user's hands. Esri would like you to tell them what you think. The best way to do that is by going to the 3D GeoNet site and posting your questions and telling them if you run into any issues. For the future, Esri has a plan to bring these voxels to the web. Esri knows that many users want to take their voxel data manipulated in ArcGIS Pro into web interfaces and web scene viewer. Also, Esri knows the tools such as props and virtual wellbores are commonly used in the extractive industries. So they do have a plan to implement them in ArcGIS Pro. These tools allow scientists and engineers to examine voxels pattern along an either vertical or a straight line, or even curving lines. They are looking at additional standard industry data types to streamline getting data into the voxel experience to begin with. Now, let's look at the question that you posted in the QA session. I'm reading the first question, Paul, if you wanted to answer it. Is there a way to calculate the volume of a filtered voxel layer? Do you want to take it?
Yeah, I can take this one. So unfortunately, there isn't any way to derive the volume of a voxel in ArcGIS Pro 2.6. However, Esri is currently working on supporting these types of workflows for the ArcGIS Pro 2.7. So be sure to look for some of that functionality in the next release later this year. Thanks.
The second question is, netcdf is not the commonly used format in the geological community. Are there any plans for using other formats? I can take this question. Esri chose a NetCDF because it's open and there are a lot of documentation about it, and there are a lot of tools available in ArcGIS Pro to bring your data into this format. They indeed have a plan to streamline getting additional standard industry data type into Voxel experience, so we can begin our working with the Voxel data with the different or additional in the industry type. Another question is, can you explain what license level is required to work with Voxel? I can take this question. For creating and manipulating Voxel, we need advanced license in ArcGIS Pro 2.6. But if you would like to share your project package with other ArcGIS Pro user, you can use the basic and standard license as well. Another question is, can I publish Voxel into ArcGIS Online? The answer is not yet. You cannot publish your Voxel into your ArcGIS Online, but Esri has a plan to create web version of Voxel so we can share it with a web scene. Another question is, can we use Voxel in machine learning or deep learning workflows? The answer is not yet. Keep in mind that this is the first release cycle, but you can tell Esri about what you think and what you want in on the 3D community website. Another question is, can you please give an example of movement layers? Can we create Voxel with wind data? If you have data that is time enabled, like X, Y, Z, T, you can create animation using time slider, exactly the same that I showed you in the demo. Another question is, will Voxel replace the space-time cube? The answer is no. There is no plan for the replacement. The Voxel is another way for looking at 3D data. So let's move on to the next part of our webinar. We have upcoming training classes related to 3D and ArcGIS Pro. If you are brand new to ArcGIS Pro, we recommend you take migrating from ArcMap to ArcGIS Pro. Also, we added the list of upcoming webinars here. And if you're interested in these topics, now it's time to register for them. In this slide, we listed the sources that we put together to make this webinar happen. And if you are interested, just use them. And we thought that it can be useful to share them with you. Feel free to contact Paul or me with any questions about voxels. For those who we couldn't take their questions, please stay tuned. We indeed follow up with you next week. Thank you for taking the time out of your day and participating in today's webinar. We will email you a recording of the webinar shortly, as well as a PDF of the slides. We would also like to get your thoughts on the presentation, so please fill out the survey that comes up when you exit the webinar. We will now stop the recording. Thanks again.